So in this video we're going to talk about ways to make alkyl halides from alcohols, and we've been discussing this in class. So we talked about these mechanisms, one type where there's a carbocation intermediate and the other type where there is not a carbocation intermediate, and we talked about converting alcohols into alkyl halides being substitution reactions where the OH gets substituted for a halogen. All right. One of the things that we talked about in detail is the need to make OH a better leaving group, because by itself it's just a really poor leaving group. And so here's the type we've already discussed, where you have a carbocation intermediate, and in this particular case you protonate the alcohol, converting OH into water, which is shown here. That water then leaving you with the carbocation intermediate. And what I want to mention here really quickly is that the rate is going to depend on how stable that carbocation intermediate is. Second type mechanism, what I'm putting in quotes as concerted, because the reactions that go through this type mechanism do have multiple steps, so they're not really concerted in that they're not only one step, but there's no carbocation intermediate. So the rate determining step is what's concerted, that step where you lose your leaving group, and in this particular case you substitute the leaving group with something else. That step does not involve the formation of a carbocation intermediate. So here I have a generic molecule ZX, where Z is what's going to make my alcohol a good leaving group, and X is going to be the actual halogen that comes in and replaces the alcohol. So when I take the alcohol and it attacks ZX, notice here Z, I now have a bond between O and Z. Whatever Z is just a generic descriptor for some atom or group of atoms, which we'll talk about in a minute. So Z is here now on the alcohol, and then X, which is the halogen, is here, and that halogen can now come in and attack the carbon and kick off the alcohol to now give you an alkyl halide, where X is a halogen and R again is a generic descriptor, and it can be any carbon containing group, and then the ZOH here in the product. All right, where Z is whatever that atom or group of atoms is that was used to make the alcohol a better leaving group. In this particular mechanism, the rate depends on the quality of the leaving group. The better the leaving group, the higher the reaction rate will be. And like I said earlier, it might be in multiple steps, but the rate determining step is concerted. So let's take a look at a reaction of an alcohol, and this is the one reaction that we already discussed, just reacting an alcohol with HX. As you can imagine, this reaction will fall into that category that we talked about, type 1, where you actually protonate the alcohol and make water. So you convert the alcohol into water. The alcohol leaves, leaving a carbocation behind, and then the halogen here that was bonded to the hydrogen in HX is what comes in and attacks the carbocation. And really, if you think back to organic 1, this is all just nucleophile and electrophile chemistry, so it might help you to refresh yourselves on what a nucleophile is, what an electrophile is, and even acid-base chemistry, because this first step is just an acid-base reaction where the alcohol is the base and HBr is the acid. So it's just a deprotonation. All right. For this reaction, tertiary alcohols work best because of the carbocation intermediate that's formed. The more stable that carbocation intermediate is, the faster the reaction is going to proceed. So let's look at another reaction. This falls into that second category, type 2, where you do not have a carbocation intermediate that's formed. All right, so if you take an alcohol, primary or secondary, and react it with thionyl chloride, which is this compound shown here, in the presence of pyridine, this is pyridine here. If you take a primary or secondary alcohol and react with thionyl chloride, that alcohol gets converted into a chlorine, right? So the thionyl chloride is a source of chlorine, and the rate determining step is concerted for this particular mechanism. It does not involve the formation of an intermediate. So let's look at the mechanism. So here's my alcohol, here's thionyl chloride, right? First step in the mechanism is for OH to attack thionyl chloride, right? So here are my arrows here, and let's look at what I get as a result of that. So once the alcohol attacks thionyl chloride, I get this intermediate here, where the oxygen from the alcohol now has formed a bond with sulfur here for thionyl chloride. All right. Step 2, pyridine comes in to deprotonate. So here's pyridine. Pyridine comes into here, deprotonates this site, and let's look at what we get as a result of that. So here, the pyridine simply deprotonated here and got protonated, and then now we still have this intermediate here. All right, and this is the important part, because this is where the chlorine that's going to replace OH is going to come from. So let's look at what happens next. Right, so step 3 is the loss of chlorine. Keep in mind, I put the energy diagram down here, and I'll talk about that at the end. All right, so now this oxygen here pushes a pair of electrons here, reforms the pi bond, kicks off chlorine, and as a result, this is what we get here, right? This is very important. This is now Z, right? OZ. We talked about that type 2 mechanism being ZX. Well, this is ZX, right? And here, at this point, I've made OZ, right? So this is my leaving group. This is the group that's going to get displaced when chlorine attacks the carbon that oxygen is bonded to right here. So let's look at the next step. What happens? All right, so step 4 is attack of chlorine and loss of leaving group. So chlorine attacks here, right? And then you break the CO bond, and these are your products here. So this is the main product, this is a side product, and eventually this thionyl chloride species here is going to deprotonate this pyridine, and the reaction can start over. All right, so that's the mechanism for the thionyl chloride reaction. This is the energy diagram. Notice, since I have 1, 2, 3 intermediates, all right, I also have 3 intermediates here. So the total number of steps in the reaction is 4 steps, right? Here, 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 and then the last step here, right? And I'll have a pop quiz in the video for this particular reaction. Let's look at another one. Let's look at reaction with phosphorus tribromide. This is another reaction that works with primary and secondary alcohols, and phosphorus tribromide is just a source of bromine, and in this reaction, your alcohol, your OH group gets replaced by bromine. All right, so again, the rate determining step is concerted, no carbocation intermediate. And then if you look at this reaction, notice I have 3 alcohols for every 1 PBr3. And the reason for that is that this PBr3 is able to donate all 3 of these bromines. So with 1 mole of PBr3, I can convert 3 moles of alcohol into alkyl halide. All right, we'll talk more about that if you have questions. All right, so let's look at the mechanism. First step, obviously, attack of the alcohol on PBr3. All right, and let's see what we get as a result of that. So we get here is ZOH, right? Now this is, you can see that now I'm set up to make the alcohol a better leaving group, the OH a better leaving group. All right, so now what's the next step? Attack of bromine at this carbon that's bonded to oxygen and the alcohol, and loss of the leaving group. All right, again, this is my leaving group right here. So let's look at what happens. Here are my arrows. Bromine is going to attack here. I'm going to break the CO bond, and let's see what I get from that. All right, and then here, this is my product. This is my alkyl halide. Notice I have the OH group that was here now bonded to phosphorus. I also have 2 bromines left, so another alcohol can come in and do this exact same reaction again and give me another alkyl halide. As always, if you have any questions, you can tweet, you can email, or you can drop by my office. Peace.